Let's do a quick recap of where we started and where we are wrapping up at this stage. I want to particularly focus on the fundamentals that we try to teach you. Recall that this course is all about machine learning. While machine learning is in itself a subfield within artificial intelligence, what we are specifically focusing on in this course is deep machine learning. Deep machine learning is a type of machine learning that leverages neural networks and lots of data in order to learn interesting patterns about that data. So these deep learning networks based on data are based on patterns that they have seen in the data. And so when we see similar patterns that repeat in the future, then they can actually make an intelligent prediction about what's likely to happen. Now, how we train these neural networks that we talked about? Well, the fundamental machine learning paradigm is this rinse and repeat cycle that we are looking at here. We start by making a guess, then we see if we got the accuracy right. In other words, is a cat or a dog, or are we saying the cat is actually a dog and the dog is actually a cat? We measure this accuracy often in terms of metrics known as top 1 or top 5. And if we are right, then we reinforce that. And if we are wrong, we correct that. And so we repeat this cycle. We continue to make a guess, measure the accuracy, and optimize based on that guess. At the heart of this pipeline is stochastic gradient descent, where the goal is you want to minimize the error. And we talked about visualizing the loss function as a rolling ball down this gradient to get it to a stable place, which is right at the bottom. In order to do that, we can adjust the learning rates, and so we can actually move faster or move slower. We talked a lot about this because there are a lot of nuances in terms of how the network learns based on the loss function. Sometimes you can overshoot and the ball goes all the way up over the other side, and then it can go back down. Ultimately, this kind of back and forth motion, you do this until you minimize this rocking, and that's happening to the ball. And that's the fundamental notion, minimizing that error. Then out of that comes a neural network. The topology of a neural network, in other ways, the number of neurons that you have, the number of layers that you have, and the way you actually connect each of these individual neurons, that topology is totally up to the developer's choice. It's totally up to you. And the key function here is that once you have a certain topology, what you want to be able to do is figure out what the weights in the network are going to be and how we are going to adjust those weights. And that's where the loss function comes in, is that you do a forward pass through this network and you make a prediction and calculate that loss. So as you are training the network by updating the weights, you're trying to minimize this loss or the error that the network is experiencing. And then we walked you through this by using the MNIST dataset. The MNIST dataset has a whole bunch of images with handwritten formats so that your ML model can look at these images and say whether it's a number that's between 0 and 9. And one thing that you did by using the Google Colab was to get these individual images, which are 28 by 28 pixels in height and width, and feed them into a densely connected network, sometimes known as MLPs or multi-layer perceptrons. And the key thing is that every neuron in there has a connection to every other neuron on the output side. And by doing that, there are lots of connections that show up in the middle. And that's why this mid-region between the two layers of neurons is extremely dense. And effectively, this network will output a probability close to 1 on whenever there's a strong indication that certain digit matches the output. So for example, when there's a 7, the output neuron number 7 is actually going to go up. And so that's a very simple thing, but it's a very powerful concept because we are going straight from an image to recognizing that image. And how do we do that? One of the key things that we learned about data is data transformations and data augmentation. Both are actually important concepts. First, we'll talk about data transformation. You took a 28 by 28 two-dimensional picture and you flattened it into a single tensor. 28 by 28 is 784 pixels. You flatten it out, and that's how many inputs you have going into your neural network. And that flattening can also be skewed in many different ways with data augmentation, which is extremely important because it's a nice way to not have to collect lots of data. For instance, a 6 is over here on the left is shown as really nice and straight as we are looking at it. And a 6 that's written at a slight angle is a different way of looking at it. And you can do all these transformations of skewing, shifting, and distorting the images without explicitly collecting, manually through human effort, more images. And instead of using, instead we can use these simple imaging techniques that can skew the data set around so that you can augment the data and effectively sometimes double or triple your data set. And by doing that, you teach your neurons to be able to be a bit more flexible and generalized through the data set that's coming in. So in addition to data transformation of putting it in the right format of the single tensor, we learned data augmentation, and that's a critical concept. And we are going to be building on this quite a lot once we get into TinyML applications in the next part. Now, we take this fundamental primitive that we have here, and then we rinse and repeat, right? We feed in a bunch of different images, one after the other, and then go on till the network reaches a stable point where the accuracy is really high or the loss is really, really low. And we learned about how to split the data set to carefully between, our test, training, and validation, which is extremely important in order to be able to make sure that you're actually not overfitting to the data that you have. Now, after that, we moved on to extracting critical insights of complex data to tease out these distinguishable features. For instance, this is a pretty complex picture on the left with a lot of rich information. And the picture on the right largely contains the same image in a very distilled format, because a filter, in effect, filters out noise. Let's say I'm only looking for the edges in that picture on the left. And the picture has edges, and it has a lot of other details in terms of the shading and the lighting and so on. So we are effectively going to be removing all of that other information, which we will call noise, with respect to what we are looking for, the edges here. And we can extract that out with this filter to get it on the right side. And only basically keeping whatever we want on the right-hand side. That's extremely important. While we know how to design explicit filters that blur, sharpen, or capture ridges and so on in images, a neural network will identify its own kind of filter parameters. And that's what it's going to be doing through the training process. And the neural networks effectively operate very well when there are a whole range of these different filters, because each one of these filters is going to try and find distinguishable features. And therefore, we tend to end up composing different filters together, layer after layer. And we did that by writing in Colab. We walked you through a variety of different scenarios where we have seen that if you take TensorFlow and you learn how to write using the Keras API calls, and one of the key things that you start off with is knowing the syntax structure of how to program in TensorFlow, which is a really powerful thing to be able to do. Second thing that you learned was how to actually compose a neural network architecture. For instance, in this particular model, you have convolutions, and you have max pooling, and then you have a dense layer at the end. And now convolutions is not just a single convolution that you have. You actually have multiple convolutions because each is effectively trying to filter on a particular characteristic. And so as you have multiple convolutions, all kind of tied together, they're filtering out data as it's moving through. Another thing that you're trying to do is pooling. You recall when you pool, you minimize the information flow that's happening from the start of the network to the end of the network. So effectively, you're trying to pick the most salient features. Every time you do a max pool, you're filtering out the most salient parts of the data. And as you move to the next filter, which is looking for something different, and then the third filter, which is looking for something different. And then you only continue to propagate the most salient features with each filtering. Finally, you get around to the dense part of the network, or sometimes also known as a fully connected network, where the fundamental idea is to be able to match the filters to the labels of the output characteristics that you and I really care about for this application. Now, with that fundamental network structure in place, which you can end up doing is repeat this network training process over and over and over again. The keyword here is epochs, which is something that we will use a lot when we are training our TinyML applications. Here, epochs means that we are going to repeat the training cycle over the data 12 times. We're going to go over all the data that we have 12 times. And so by doing that, we actually get a much better accuracy because the more time we train, the better it is. Now that's really great. So, but remember over here, training for longer is not always the right thing. There's often a trade-off where overfitting of the data or any other thing. They remember that when you're training, you're usually going to be doing something that's very costly over here, because you're training for a longer time, you need a lot of resources. So that drives the cost up through our training process. And over the course of your experience in machine learning, you will be using CPUs, GPUs, TPUs, DSPs, NPUs, neural processing units. There's a wide variety of kinds of new hardware that have come about. I'll try to teach you a little bit about this as we get into more advanced concepts later in the course. Now, remember that all these processing units are then packaged into big data centers, and as these pods, as Google likes to call them, are what are powering some of the machine learning services. So when you train your network in a Colab, it might very well be running on one of these servers for all you know. Now, that's all on the algorithm side. And now, one of the key things is that the fundamental knowledge that you acquired has now been repurposed so many times by these big companies that are building deeper and deeper and deeper neural networks, so much so that the number of parameters that are involved in the machine learning models are so big, it's on the order of billions of parameters now. And that's what this chart is showing over here. It's showing the state of the art neural network models for natural language processing. It has billions of parameters in terms of number of neurons. It's so big that it can actually learn a lot of information. So this computational capability on one hand, and having a lot of deep networks and new architectures allows us to learn a lot of things. And that's really, really amazing. One of the things that's been happening, obviously, is from AlexNet, which started out in 2012, as you might recall. Models have been getting better. In other words, they've been improving in terms of accuracy. And essentially, we're going up the y-axis over here. We talked about AlexNet moving into VGG as a big major milestone. Why did we say that? Because as you saw, the VGG models improved accuracy, which is going up the y-axis. And on the x-axis, the amount of computational horsepower. And the size of the circle tells you how big the model is. As models get bigger, we wanted to make them smaller because we are becoming more aware of the resources and how costly they are. It does cost a lot of money to train these large models, sometimes tens of millions or even $100 million. So we want to make them smaller. We're making them smaller does not mean that we lose accuracy. We're totally able to boost the accuracy as we have seen in the past few years. For example, in going from VGG to ResNet, we actually were able to boost accuracy while keeping the models smaller. So we got, the cake and ate it too. But then as smartphones came about, we felt the desperate need in order to make the models even smaller. So we needed to shrink them down further. Now the question is this: as we move from big data centers to mobile devices, to the next mirror horizon or the next ecosystem or the tiny low-powered chip, how are we going to make these models? And if you recall, a typical mobile net model, which is designed for smartphones, for instance, occupies around 17 megabytes. That's a lot of memory still. And in fact, the microcontroller, for example, that we'll use in part 3, which is a typical microcontroller, has only about 256 kilobytes, not megabytes, kilobytes. And that's an order of magnitude difference between where we are today and where we need to be in the future. And if you want to deploy machine learning to these billions of microcontrollers, that's going to mean that we need to do something big. And that means that we have to innovate on machine learning model stat. That we have to figure out not only how to make the machine learning models smaller, but we also have to figure out how to cram these models into tiny little hardware devices with limited resources. And that's all on the machine learning algorithm side again. But remember, as I told you, there's the embedded system side. So we talked about this and we tried to really understand what are the fundamental constraints in a microcontroller compared to a microprocessor. For instance, microprocessor is running machine learning models in the cloud versus microcontrollers, we want them to run at the edge. From compute to memory to storage to amount of power they consume, there's at least an order of magnitude difference between the capabilities of a microprocessor and what capabilities these tiny machine learning microcontroller processors are going to do. So this really seems bad, right? I mean, how are we going to make this big jump? Now, remember, we want you to do this because tiny devices are everywhere, right? In the future, believe it or not, I won't be surprised if we put machine learning models on a tiny device, on a coin cell battery, and we forget about it. We just forget about it. It's processing, it's collecting information, it's doing interesting sensing things, and someday it just biodegrades. And so we are not even polluting the earth. And so these are some of the key things that happen because power is critical in these systems. We understood, for instance, how vendors have to make trade-offs in how to build these microcontroller devices. So in an embedded system, you tend to have a lot of fragmentation, hardware fragmentation, software fragmentation. We talked about how the floating point unit is present in one device, may not be present in another device. What does that mean? It means that you have to recompile all your code and update it for the next special device. Every device is a special device, and that becomes a major problem. Why do we do something like this which breaks this compatibility, right? We do it because it lowers the cost compared to making one device for everything. It lowers the amount of power consumption needed because that device only does that specific thing. Like it only works on elevators or washing machines, or it only senses certain sensors and outputs, certain outputs, right? So it's all essentially reducing the engineering effort. And this also means that we can crank out these little devices, like no other. They are not incredibly complex, like a one-size-fits-all microprocessor. But the trade-off is portability, which introduces problems to us that we will learn how to address in part 2 and part 3 as we get into the hardware. And remember, it's also, I talked to you about, how you have operating systems now as, that are very rich on the laptops and the servers, and these operating systems just dominate these markets. And same thing with mobile, the mobile ecosystem. You have iOS and Android, and they're amazingly dominant, and they basically run the entire world, but it essentially makes it easy for application developers to make, millions and millions of apps. But what happens when you go to an embedded system on Mbed OS or FreeRTOS? These are operating systems that exist, but not every embedded system uses them. Sometimes there's no operating system. There's no concept of running multiple programs on the same embedded system. You just wanted to do, people detection and nothing else. Every device is different because every application is different. So this creates a massive problem of being able to systematically make models smaller and being able to deploy them efficiently across a wide class of these microcontrollers. But don't worry, right? All this said, we have solutions that are coming about, and that's what we're going to really learn next. And in this course, as we learn to make models smaller, we also learn about efficient runtimes, right? What is the software systems under the hood that are allowing us to run machine learning models efficiently? And as we understand the capabilities of the hardware, we realize that we need to co-design between the models, the runtimes, and the hardware. We need to be aware about these constraints, so we design things accordingly. And remember, I promised you one thing when we started off this course, and it is that we are going to learn not only about each of these individual layers, but we're actually going to learn about the interactions that happen between these layers. And that's extremely critical because that's what's going to make you stand out from the rest. Now, with that said, I'm going to leave you with these things to reflect upon, and I'll see you in part 2.